Welcome to Avantier's webinar on High Numerical Aperture Objective Lens and their critical role in quantum computing. In the realm of quantum computing, microscope objective lenses serve functions far beyond conventional imaging. High-NA lenses are indispensable tools that enable the precise optical interactions required for quantum state control and measurement. Their superior spatial resolution and light collection capabilities are essential for achieving the fidelity and scalability demanded by next-generation quantum technologies. Whether used in neutral atom arrays, trapped ion systems, or photonic quantum processors, high-NA objectives allow for accurate light focusing and efficient photon collection. This optical precision is vital for manipulating individual qubits, performing reliable measurements, and building scalable quantum architectures. High-NA lenses are specifically designed to optimize light collection at steep angles while minimizing optical aberrations across designated spectral bands. Their construction requires precise alignment of multiple, finely polished optical elements. The result is a diffraction-limited optical system capable of high-resolution focusing, efficient fluorescence collection, and controlled beam shaping, making them ideal for quantum applications. These objective lenses are also engineered for compatibility with demanding environments such as vacuum chambers and cryogenic systems. They are typically integrated into optical setups built for long-term experimental stability, often involving vibration-isolated platforms and piezo-actuated stages for nanometer-level positioning accuracy. High-NA objectives are key to tightly focusing excitation beams and efficiently collecting fluorescence or scattered light from qubits. They integrate seamlessly with beam steering modules, imaging sensors, and atomic or ionic traps. In neutral atom systems, high-NA objectives enable site-resolved addressing, lattice imaging, and single-atom detection. In ion traps, they support tight beam delivery and high-efficiency photon collection. In photonic quantum platforms, these lenses enhance coupling efficiency into waveguides and detectors. Across all architectures, they help preserve system coherence, improve spatial resolution, and maintain signal integrity. When selecting a high-NA objective lens for a quantum application, engineers must consider factors such as spatial resolution, wavelength compatibility, field of view, working distance, mechanical interface, alignment stability, and environmental robustness. Seamless integration into the existing optical path is also crucial to maintaining system performance. Thank you for joining us. We hope this session provided valuable insight into the role of high-NA objective lenses in advancing the performance and reliability of quantum optical systems. For design consultations, system integration guidance, or custom configuration discussions, please don't hesitate to contact us for expert consultation and support. See you in the next webinar.
Avantier, empowering optical innovations.